As we bring the Mathematics of Artificial Intelligence playlist to a close, we'll be looking at the reinforcement learning trick behind AlphaGo. I mean, I might make another video if something comes up, but here I'm talking about the reinforcement learning trick behind AlphaGo. Reinforcement learning is one of the branches of machine learning because machine learning is fundamentally divided into supervised learning, where we use labeled data, unsupervised learning, where you have unlabeled data, and of course reinforcement learning. Of course, some people throw in semi-supervised learning sometimes, but that's how it goes. So if you want to know more about this, you want to check my playlist on machine learning with EJD. So I broke down all these aspects here and took different algorithms and explained the codes and all of that. So here we are talking about the reinforcement learning trick behind AlphaGo. So, AlphaGo became famous because it demonstrated that a machine could learn to play the ancient game of Go at an extraordinary level. So, Go is an ancient Chinese game, by the way. Just like computers have come to play chess. I mean, the computers even play chess better than some chess masters like that, right? So, same way, Go, which is a complex ancient Chinese game, has now been played, by computer via AlphaGo. So, but AlphaGo did not simply memorize good moves, right? So, I think before I even start going too deep into this, I just want to see what the whole Go thing is about. I want to see what Go is about. Go, Go, yeah. So it says Go can refer to the open source Go programming. No, Go game. I'm talking about the Go game. Go game. Exactly. So Go, known as Ego in Japanese, or Weichi also in Chinese, and Baduk in Korean, is an ancient two-player strategy board game. Two players take turns, placing black and white stones on the grid. Intersections of a board on the grid intersections of a board surrounding more territory than the opponent. So basically, this is what the image looks like. This is Go. So in fact, some people end up becoming masters of Go like this. So it's a really complex game, not so easy to play. But AlphaGo has shown that computers can actually play the complex games men play. I think there was a time I was watching a documentary on Japanese TV, and one master, I think I don't know if it is this Go or some other game that looks so much like this. So computers have come to play these games as complicated as they might be. So AlphaGo did not simply memorize good moves. Its power came from combining several mathematical ideas. For instance, talk about states. States talk about what does the current game position look like. Then actions. Now, based on states, you take actions. So, what moves are available to make based on this current state? Then you talk about rewards. Was the decision good or bad? So, if you play and then you give your opponent some advantage, you cannot recover from that. That's not a good move. So you get negative reward for that. But if you make good moves that help you can actually be rewarded positively for that. So then there are policies to which action should the agent choose. Then there are value functions where how promising is a position. Then optimization, how can the agent improve its decisions? And exploration, should it try something new? I think we came across the idea of exploitation and exploration. Exploitation is the idea of doing what you've always known to do, and exploration is trying something new, like that. So I think that's closely associated to the idea we saw when we're talking about when we're talking about PageRank, yeah, PageRank. So under PageRank, we saw the place of the place of using a web link, using a hyperlink, or going to a totally new web page, and that is called what's that called now? I'm trying to remember the name. Uh, Interesting. I've forgotten what that is. Okay, but I think I think that was the second to the last video or something like that, where we're talking about the eigenvector trick behind Google search. I'm trying to really remember that. Okay, I mean you can check that up to see. So we have exploration. Should it try something new? Then there's Monte Carlo search tree. How can it look ahead before choosing a move? So can you look ahead before choosing a move? Can you think of a great move to make before you even make the move? Then there's self-play. How can it generate enormous amounts of training experience? So the central idea is an intelligent agent learns by making decisions, So as you make the decisions, you observe the consequences and then receive rewards, whether positive or negative, and improve future decisions based on whether you receive good or bad reward. So if you receive bad reward, you don't want to make that move again. If you receive good reward, you want to make that move or even get better on that particular kind of move. So you can also see this. I think one of the last videos I made on reinforcement learning under the machine learning playlist. So these kind of ideas were explained there. So, but this now comes from I mean, this is also another approach at it based on the idea of how AlphaGo has come to play Go, which is such a complicated game and that is it's able to do using a lot of mathematical concepts. So the question again is, what is reinforcement learning? So reinforcement learning is a framework in which an agent interacts with an environment. Well, in simple terms, right? Think of parenting. You Anytime your child reads a book, you give your child money, right? So anytime your child fails to read, they don't get the money, something like that. So because you give them money, so it helps them to enjoy reading. So that's basically the idea of reinforcement, right? So because of reward, the reward can help you you know, to imbibe certain habits that actually attract the reward. So reinforcement learning is a framework in which an agent interacts with an environment. At each time step T, the agent observes a state S sub T, chooses an action A sub T based on the state, and then receives a reward R sub T plus 1 and moves to a new state sub T plus 1. So there's an agent. The agent observes the environment and looks at what is happening in this environment and chooses a state of action. The agents observe the state, and based on the state, it chooses a particular action. And taking the action, it gets a reward, whatever that is, negative or positive reward. And then, based on that negative or positive reward, the agent changes state. So the interaction can be represented as S of T going to A sub T, going to R sub T plus 1, and a new state, S sub T plus 1. So for Go now, the state is the current Go board. So when you get to the Go board, that's maybe when you imagine starting a chess game or something like that. Or there's also this other one. I think it's called draft, or maybe there's another name it's called, right? Let me see. I think that's the game. I played that a little bit growing up. I don't know if what it's called is draft game. Oh yeah, maybe it's draft game. Yes, exactly. This is yeah, okay. I think it's called checkers. Exactly. So this is it. This is draft game. So it's called checkers. So yeah, I grew up playing this a lot. So like this. So when the game starts, this is what the whole thing looks like. Something like this. So you have your pieces arranged this way, and you have to move. So you have to move in such a way that you finish all the pieces of your opponent. So whoever has any, even if every piece of your opponent is gone and you still have at least one left, you have won the game like that. So that's a very close example to the idea of Go. I think Go is probably even a bit more complicated than that. So the current state. The state is the current Go board. The action is placing a stone at a legal location. So you place it at a particular location. Of course, you can't place it everywhere, but a particular one. Then the reward is ultimately winning or losing the game. And the policy will talk about the strategy for selecting moves. So what are you thinking about before you select the moves? That's your policy. So then the agent's objective is not necessarily to maximize the immediate reward. So you may not get the best reward right now, but ultimately you want to win the game. I remember in the game of checkers or draft, right? Sometimes you lure your opponents by giving them some advantage. So they may think. So when you give them the advantage, they think they are getting you. But by the time they are done, then you now get even okay. Maybe you give them the opportunity to take out five of your pieces. And by the time they are done taking five out, you end up taking six of theirs out. Like even getting that one advantage is a reward. So you may not have immediate reward. So giving them five is not like a reward, but you can, give them that so you can get something even better. So the agent's objective is not necessarily to maximize the immediate reward. Instead, it wants to maximize the long-term reward. So the reinforcement learning loop looks something like this. So the basic reinforcement learning loop is you have the state S of t, choose an action S of t in the environment, and then you get a reward and moves to a new state. So the agent repeatedly performs this same process over many experiences. It learns which actions tend to produce better outcomes. So the more you play these kind of games, the better you get because so you now find a way of learning tricks that gives you the reward that makes you win all the time or as many times as possible. Then why rewards matter? Suppose an AI is playing Go. A game might contain hundreds of moves, but the final outcome would simply be a win or a loss. So the reward is +1 for win, -1 for loss. This creates a difficult learning problem. So imagine the agent makes move 37. So 37th move. It does not immediately know whether move 37 cost the eventual victory. The reward may arrive much later. So you may not see the reward immediately. So you may even be gaining some advantage in the beginning and at the end of the day, you don't still win the game. So because the reward may arrive much later. So this is known as the credit assignment problem. The agent must determine which earlier decisions contributed to the final result. This is one of the fundamental challenges of reinforcement learning. So you want to know which of the early actions led to the reward or the kind of reward you got. So immediate reward versus long-term reward. Consider a simple game. Suppose an agent receives R1 is 0, R2 is 0, R3 is 0, and R4 is 10. So if we simply maximize immediate reward, the first three actions appear worthless. So you get no reward at the first three steps, and then you get 10 points at the fourth step. So if we simply maximize immediate reward, the first three actions appear worthless, but they may have been necessary to obtain reward of 10. Therefore, reinforcement learning considers future rewards. So future rewards matter more than immediate reward in reinforcement learning. So a common definition of total future reward is the return G sub t, which is R sub t plus 1 plus gamma, R sub t plus 2 plus gamma squared, R sub t plus 3, and so on and so forth, where gamma lies between 0 and 1, and it is called the discount factor. So for every subsequent reward, you have gamma increasing like that. So if gamma is equal to 0, the agent cares only about immediate rewards. Okay, so if gamma is 0, the agent cares about immediate rewards. But if gamma is close to 1, the agent strongly values future rewards. And like we've said already, future rewards matter more than immediate reward in the game of in reinforcement learning in general in reinforcement learning. So we look at this example to drive home that particular point. Look at this now. Suppose first reward is 2, second reward is 5, and third reward is 10, and the discount factor gamma is 0.9. Then we say G sub 0, the reward, the discounted return will now be 2, the initial one plus 0.9 times 5 plus 0 times 9 squared times 10. So that ends up giving us 2 plus 4.5 plus 8.1. So the discounted return is then 14.6 after applying the discount factor. So and of course we can write a simple program for that. So you have the rewards 2, 5, 10, and the discount factor is 0.9. So the initial G is 0, right? So for I in reward, for every each of these rewards, so this I indexes each reward. So for I in reward, enumerate the rewards, and then G plus equals gamma star star I times reward. So it's more like uh you have the G initially plus gamma, and then later you then have gamma squared time gamma raised to power I. So the first gamma now, so you have gamma plus gamma raised to power 1 times reward. Then again it goes and you have plus gamma raised to power the next time, which is power 2 now of reward and so on. And by the time you run this, you get the discounted return of 14.6, just like what we have up here. Now let's talk about the value function. So instead of explicitly calculating every future sequence, reinforcement learning can learn a value function. So the state value function is v pi of s, which is expected sub pi of g sub t, given s of t equals 0. Given that state is s, so the discounted return you get, given that the state is equal to s, the expected value of that discounted return is what is given by this value function. So it answers, if I am currently in a state s and policy pi and I follow policy pi. How much future reward should I get? So that's the expected value of the future discounted return given the current state and the policy pi. So for AlphaGo, the value of a board position can be interpreted approximately as how likely is this position to eventually lead to victory. Then we have the action value, the action value function. Sometimes you want to evaluate not just a state, but a particular action. So this gives the action value function. So you have pi, q pi of s comma a equals the expected value given the policy pi of the discounted return given state s and action a. So it's answer. So in this case now, the other time we saw what we saw was just the value function. Now we have the action value function. So you have both the action and the state together. So now the action has now been added. So it answers if I am in state s and take action a, how good is that decision? So and that is going to be dependent on the expected value of the discounted return you get. This is extremely important for games. For example, Q of S move A is 0.72 and Q of S move B is 0.43. The model would generally prefer move A because move A gives a higher reward, almost a higher reward than move B. So see this example, choosing between two actions now. Suppose the game has two possible actions. A is 0.80 for the reward. The reward of A is 0.8, the reward of B is 0.45. So a greedy agent chooses A star, which is argmax over A of QS comma A. Therefore, A star is equal to A. So the optimal action will be A because it gives that reward. So for a greedy agent, right? For a greedy player, so to speak. So the mathematical idea is simple. Choose the action with the highest estimated long-term value, but there is a major problem with that actually. So what if our estimates are wrong? What if these estimated rewards are not really correct? That leads directly to the idea of exploration. So you may have to explore. So, but before we talk about exploration, let's talk about exploitation. Exploitation is more like sticking to the action you have always known that works. So exploitation means choosing what currently appears to be the best action. Mathematically, A sub t, that's action at time t, is equal to argmax over the action for q at state t and action A. Suppose the agent estimates QS comma A is 0.8, Q of S comma B is equal to 0.6, and Q of S comma C is 0.3. Exploitation chooses, if you want to exploit, you just go for a 0.8. So you go for action A, which gives 0.8. And this is actually sensible, but it can cause a serious problem. And then that leads to the exploration problem. Suppose the agent has only tried actions A and B before. It estimates QSA is to be 0.8, QSB is 0.6. It keeps choosing A because A is always giving a better return. But suppose there's another action C whose true value is actually 0.95. You will never know if you keep exploiting. So until if you don't explore, you won't find, maybe you won't find anything if you actually explore, but you can also find something that is better than what you already know. And that is why it's always important for us to keep open minds. So if you just stick with only what you know, you may not learn anything new. So the agent will never discover if it's always exploit its core. The agent will never discover this new value if it's always exploit its current knowledge. So this is the exploration exploitation dilemma. So we have it. I think we've seen it elsewhere. Now we are seeing it here. So this is the exploration exploitation dilemma. The agent must balance exploitation and exploration. Exploitation, you use what you already know works, and exploration is truly try on certain actions that might be better. So this idea is central to AlphaGo. So the whole idea of exploration exploitation dilemma applies a lot to AlphaGo. So let's look at an epsilon greedy exploration. One simple exploration strategy is epsilon greedy with probability 1 minus epsilon. You choose the best action. So with probability epsilon, you choose an exploratory action. So for example, if epsilon is 0.1, then it means that 90% of the time you need to exploit. That's 1 minus epsilon now. But 10% of the time you explore. So you explore with probability epsilon and you exploit with probability 1 minus epsilon. Of course, there's every high chance that what already works is actually what works best. But of course, you should give yourself some allowance to try something new and you might just discover something that works better than what you already know. So the basic idea is action selection is equal to mostly exploitation plus occasional exploration. And that is how life should be lived. So most of the time, choose what works, and once in a while, try out new things to see if there's something better than what you already have. I also apply that to my music. I love listening to music on YouTube a lot. So, and I have some go-to music. So sometimes I just allow myself to, scroll to keep scrolling. I might just, and sometimes I just discover some kind of music I really like that I never would have known existed if I didn't explore. So, and what we did up there now, you can have a very good example, import random. So you have Q is A 0.8, B 0.6. Maybe you're only used to A and B, and there's actually a C out there with rate 0.95, which you don't know. So if the if epsilon is 0.1, right? Uh the epsilon which talks about how you should explore is 0.1. So you have a 10% chance of exploring. So if you now choose randomly, choose any random epsilon. So if whatever random you choose is less than the epsilon, then the action should be random choice. Then you list all the Q keys. We have the keys here, all the Q keys, and print exploration and action. Else, if that doesn't work, then you choose an action, another action, which is you stick to your exploitation like that. So if you choose a random value that is less than epsilon, you explore. If not, you choose your exploitation. And if you do this here, you can then actually go for exploit. You exploit action C in that case. Now, why AlphaGo needed more than random exploration? Random exploration works reasonably well in simple environments. So Go is not simple. The number of possible game positions is enormous. Therefore, simply trying random moves would be extremely inefficient. Even in the game of drafts, you can't just keep moving without strategy. You have to be strategic in your moves. So AlphaGo needed a much more intelligent form of exploration. This is where Monte Carlo Tree Search becomes important. That's MCTS. So the search can be like an exploration. Imagine the current board position to be this now. You have A1, A2, B, B1, B2, C, C1, C2. Instead of immediately selecting a move, the system can investigate possible futures. So before you select an action, think of what, if you play, think of what your opponent is going to do that might actually do it. So you're not only thinking for yourself, you're also thinking for your opponent. You're also thinking what the possible moves your opponent might make that might profit you or damage or not affect you. So this creates a search tree. So each node represents a game state and each edge represents an action. So these are game states and each of these now are actions. Each edge represents an action. So this is an edge, right? These are edges now. So the deeper the search goes, the more future consequences can be investigated like that. So let's talk about Monte Carlo search tree. So Monte Carlo tree search rather repeatedly performs four conceptual operations of selection, expansion, simulation, or evaluation, and then there's back propagation. Just like we know in machine learning or artificial intelligence in general, backpropagation is simply the whole idea of, after making a prediction, you want to see how close your prediction is to the reality. And that the difference between that is what backpropagation is trying to optimize, to wants to make it as low as possible. So the process looks like this. You have selection, expansion, evaluation, backpropagation, and then you repeat until you get what you want. So the goal is to spend more computational effort investigating promising moves. Suppose the search statistics are as follows. So you have moves A, B, and C. So move A visits N 100 times, move B 20, move C 5, and the estimated values are 0.6, 0.65, and 0.55. So move A has been explored extensively because there's 100 moves had been made. So, and it comes with 0.60. Then move C has hardly been explored because it has only been made 5 times. So then the search algorithm should consider both the value and the uncertainty. So this represents much more sophisticated form of exploration because the algorithm does not simply choose the move with the highest estimated value. It also considers whether a move has been sufficiently investigated. All right, so this has been sufficiently investigated. So there's a high chance of always wanting to go for move A because it gives 0.6. But a move that has been made 20 times and gives 0.65, though it looks higher than A, but it may not be as reliable as A like that. So because we don't have sufficient data to show that it is actually that reliable. So um so the value and certainty idea, then this represents a much more sophisticated form of exploration because the algorithm does not simply choose the move with the highest estimated value. It also considers whether a move has been sufficiently investigated. So let's talk about the UCT idea. A classic Monte Carlo tree search selection rule is upper confidence bound for trees. Upper confidence bound for trees, that's UCT. So UCT, given a state and action, is simply W of S of the state and action over N over of the state and action plus C multiplied by the natural logarithm of N of S and all over N of S comma A. So WS comma A is accumulated reward. N is the number of visits to action A, then NS is the number of visits to the parent state, and C is the exploration constant. So the first term represents WSA, WS comma A over N over S n of s comma a. So the second term represents exploration. So this is exploitation right here, and this is exploration right here. Therefore, UCT is actually exploitation plus exploration. So the upper confidence bound for trees is actually a combination of exploitation and exploration, just like what we saw with PageRank, like that. Yeah. So what the exploration term, why the exploration term works, right? Notice what happens when n of s comma a is small. That is in that case, now when it is small, you have 1 over n of s comma a will be very large. If this is small, then 1 over it will give us something pretty large. Therefore, the exploration bonus becomes large in that case for a small value of n. So rarely visited actions receive an incentive to be investigated. But as the action is visited repeatedly, that is, as n approaches infinity, 1 over n will approach 0. And therefore, we can say that square root of ln n of s over n of s comma a will approach 0. So they are 0. So the algorithm gradually shifts from exploration towards exploitation, like that. So this is a beautiful mathematical mechanism. So what we are saying is when n is very small, this exploitation dominates, like that. So, but when n becomes very large, okay, exploitation plus exploration. So when n is very small, right? When n is small, so this whole thing is really large. So exploitation dominates. But when n becomes very large, so this for small n, right? This part is big, so exploitation dominates. For big N, this part goes to 0. So exploration, I think I'm missing something up here. Yeah, okay, I think that's what we already have here, right? So yeah. So as the action is visited repeatedly, right? As n approaches infinity, therefore, we have this particular point goes to 0. But when it's small, yeah. So in this case, then the algorithm gradually shifts from exploration toward exploitation. This is a beautiful mathematical mechanism. Uncertain actions receive attention, while well understood actions increasingly compete on their estimated value. So if an action has not been tried out, you want to try it out until you know what it gives. But the actions you already know, you go for them based on what you already know about them. So let's take a UCT example here. Suppose NS is 100 and consider two actions. Action A, W of WS comma A is 60. Then the N is N of S for action A is 100. Then action B, WS of B is 14. And NS of B, N of S comma B is 20. And C is 1.4. In that case, for action A now, we have Q sub A. So Q sub A now is actually 60 over 100. That is 0.6. And the exploration term then becomes 1.4 times in 100 over 100, like that. Then for B now, QB is 14 over 20, and that gives 0.70, like that. So although B already has a larger estimated value, so B is larger than this, like that. Its exploration bonus is also substantially larger because it has been visited fewer times, like that. So uh, this is precisely the behavior we want in that case. So looking at this now, so import the math library. So let's say n parents, you have 100 and C is 1.4. You have three moves A, B, C. So win. So for A, 60 wins and 100 visits out of 100 visits. For B, 40 wins out of 20 visits. And for C, 2 wins out of 5 visits. So you can see the visits coming down like that. So for move, so for every move, for move in data, in this data now, for move and data in move items here, the items we have right here, the value is equal to data, the number of wins all over the number of visits. So data of visits, like that. Then the exploration will now be C times the square root of the math log of n parent, all over data, all over the total number of visits, in short. And then UCT can then make whatever value you get from here plus exploration, and then you can print that. So if you print this now, from what we already have, so for A, um For move A now, the value is 0.6, exploration is 0.3, and UCT is 0.9. B, you have 0.7, 0.672, yeah, and you get 1.372. Then for C, 0.4, 1.344, and the UCT is 1.744. So though C has fewer visits, but it gives the highest UCT like that. And then we can talk about expansion. So once Markov chain tree search selects a promising path, it can expand the tree. So if the current is A going to A1, A2, if A1 has not been explored, the if A1 has not yet been explored, right, the search creates that new node. So the tree gradually grows around promising parts of the game. This is much more efficient than exhaustively exploring every possible future. So you just go as you learn on the game, and that's the whole idea of reinforcement. So if you play and you get a good reward, you want to keep playing more of that. And then, of course, once in a while, you try out new things, and you might just find out that some of them are even give better reward than what you are used to already. So you always have that exploration exploitation thing going on. So you have evaluation. Traditional MCTS, that's Markov chain tree search, can use simulations to estimate the outcome of a position. For example, imagine simulating many games from a particular position. Suppose 700 simulations result in wins and 300 simulations result in losses. Then the estimated value could be V of S, which is 700 over 1000, which is 0.7, and the position appears favorable. But AlphaGo introduced something much powerful. Neural networks could help evaluate positions and guide the search. This gives us two important questions: which moves are promising, and how good is the current position? And then we talk about policy and value networks. AlphaGo used neural networks to help answer two important questions. Policy question: which moves are promising? A policy network estimates probability of action given the state. So that talks about promising actions now. Then value question. Then there's the value question. How likely is the current position to lead to victory? So a value network estimate V of S. So the policy network helps determine where to look, and the value network helps determine how good a position is. Then we have policy versus value. So for talking about policy versus value, imagine the current board allows 100 legal moves. A naive search could investigate all of the 100 moves. That is, I mean, somebody who doesn't know so much. So a policy network, or we can say an agent that doesn't know so much, right? A policy network might estimate the moves A, B, C, D, and others with the policy probabilities as follows, and the highest of them is A, and like that, followed by others. So the search can prioritize moves A, B, and C. Thus, policy network implies where should I look? That's the policy network. While value network is how good is this position I'm looking at? So you have to compare the policy and the value. Then let's talk about policy optimization, which of course I talked about during under the playlist for machine learning. Suppose the neural network outputs probabilities pi sub theta of action given S, where theta represents the neural network parameters. The network can be trained to produce high probability for good moves, and a common supervised learning loss is cross entropy. So we have L of theta, which is minus summation over all the actions for YA log pi sub theta of A given S, where YA represents the target move distribution. The parameters are updated using gradient descent. So which is, I mean, which we already always know. And that's what keeps happening until we get, because we want to minimize the loss. Here, theta talks about the model parameters for the neural network you might be using. Alpha is the learning rates. And then you have grad of theta L is the gradient of the loss now. Then we have reinforcement learning objective. So ultimately, the system wants to maximize expected return, J of theta, which is expected value given the strategy and the parameters of the discounted return, G sub t. So the optimization problem becomes, theta star is add max over theta of J of theta. In other words, find the parameter that produces the strongest long-term game performance. This is the central optimization problem in reinforcement learning. So at the end of the day, you want to find the parameter that produces the strongest long-term game performance. Then we have 45.15. So policy gradient intuition. Suppose the network chooses an action and eventually wins. That action sequence receives positive feedback. A policy gradient method can increase the probability of actions associated with successful outcomes. Conceptually, you have theta plus alpha G sub theta, grad sub theta log pi sub theta, alpha A sub t given S sub t, leading to a new theta altogether. So it's like you have the old theta leading to the new one. So following technically the idea of gradient descent. So if G sub t is large and positive, like this, successful actions receive stronger reinforcement. If the outcome is poor, their probability can be reduced. So this produces simple learning principle. Actions associated with good outcomes become more likely. Actions associated with bad outcomes become less likely. So if you read and you get paid $5, and if you don't read, you get paid nothing. So you want to read so that you can get paid $5, something like that. So that reinforces the habit of reading in a way. So, and then we have the policy gradient example. Suppose the network assigns pi sub theta of the action given the static 0.4. After choosing A, the agent eventually wins. Suppose the discounted return G sub t is 1. The update encourages the network to increase the probability of A in similar states. If instead G sub t is -1, this is a win, this is a loss now. The update pushes in the opposite direction. So it means going for action A doesn't always help. So it doesn't help, right? So the exact size and direction of the parameter update depend on the gradient, but the underlying principle remains. Good outcome implies increased probability of useful actions, and poor outcome decreased probability of harmful actions. Then let's talk about the Bellman equation. So a central equation in reinforcement learning is the Bellman equation. For a policy pi, then the value function also for pi of at a particular state is actually the expected value of the reward at time t plus 1 plus gamma v, talking about the policy at state t plus 1, and all of that given this current state S. So this says the value of the current state equals the value of the current state, right, equals the immediate reward plus the discounted value of the next state. So this recursive structure, so it means even the next state is already affecting this state. The reward of the next state affects this current state like that. So because you are taking an action based on the reward you are going to get. So this recursive structure is extremely powerful because it allows a difficult long-term problem to be expressed through relationships between neighboring states. So let's talk about the Bellman equation example. Suppose R is equal to 3, reward is 3, and the next value state value is and the next state value is V of S prime is 8. So let gamma be 0.9. Then V of S will be the the next reward plus 0.9 times the next the value of the next state. So VS now is 10.2. So the current state is worth 10.2 in reward. So, and then that takes us to the idea of Q learning. Another fundamental reinforcement learning update is the Q learning rule. So we have Q of S comma A. You have all this resulting to this Q of S comma A plus alpha into R plus gamma. Then you take the maximum of Q at S prime A prime over all the A's minus Q of S comma A. So the quantity inside the bracket is the temporal. So the quantity here is the temporal difference error. So this is some kind of balancing factor you have there. So delta then is equal to R plus Y max of all of this. So this whole thing now, so this whole thing we call it delta. So that's the temporal difference error. So the object is therefore Q comma S of A, is arrived at from the old Q comma S of A plus alpha multiplied by the temporal difference error. So interpreting the temporal difference error now. So the temporal difference error compares the current estimate Q of S comma A with improved target R plus gamma of the maximum Q, over A prime. If delta is if delta is greater than 0, the action was better than expected, right? If delta is greater than 0, but if delta is less than 0, you see this delta is going to downplay this part of the game, right? So if delta is less than 0, the action was worse than expected. Therefore, delta is equal to prediction error in value. So the agent uses this error to update its future decisions. So we have a Q learning example here to deal with. Suppose Q of S comma A is 4. The agent receives R equals 2 and estimates that the best future action has value 8, like that. So let gamma, the discounted value, the discount factor is 0.9 and alpha is 0.1. So the target is 2, the 2 R here plus discount factor times 8, and that is 9.2. Then in addition to that, the new estimate then becomes So you then have delta. Delta is 9.2 minus 4. Delta is 9.2 minus 4. And so the new estimate is Q new equals 4 plus 0.1 times 5.2. And this is 0.52. So Q new is now 4.52. So the Q we had was 4 before. So the model increases its estimate because the outcome was better than expected, like that. So from 4, we have 4.52. And this is the code taking care of that. So you have Q 4.0, reward 2.0, gamma 0.9, alpha 0.1, future value is 8.0. So the target now is the reward plus gamma times future value. So then the TD error, time difference error, is now the target you have here minus the original Q. So the Q new will now be Q plus alpha times the time difference error, temporal difference error, I think. Uh, yeah, that's temporal difference error. Yeah. So, and then you have, so of course you see the target is 9.2, the error is 5.199, roughly 5.2, and then the updated Q is 4.52, like that. So now the question is, why is Go difficult? So Go is an extraordinary reinforcement learning problem. So the board is 19 by 19. So therefore, they are initially up to 19 times 19, which is 361 board intersections. But the difficulty is not merely the number of legal moves. The number of possible game sequences grows explosively. So if there are approximately B possible moves at each step and game has depth D, naive search could involve approximately B raised power D possible sequences. This is called the combinatorial explosion. So that is why Go is difficult. So, and then why does brute force fail in that case? Suppose the simplified game has B is 100, so possible moves per position and the search depth of D is 10. Then naive exhaustive search would consider roughly 100 times 100 raised power 10, which is about 10 raised power 20. Because this is 10 raised power 2 times 10 raised power 2 raised power 10, that's 10 raised power 20 of possible sequences. That is, you have this is of course, this is thousand, this is million, this is billion, this is trillion. Would this be quadrillion? I think I mean, this is such a big number. In fact, let me even do this. So this is, so it's like 1 billion million. No, 1 trillion billion. That's what it is. 1 trillion billion. Let me ask, what is 1 trillion billion? Maybe it's sextillion or something. What is 1 billion trillion? 1 billion trillion. That is sextillion, yeah? That's sextillion. That's 10 raised power 21. I think that's 21 zeros. Sextillion. This 3, 6, 9, 12, 15, 18, 18. Uh, that's 10 raised power 20, right? So what is 10 raised to power 20? 10 raised to power 20 called as a number. Okay. 100, that's 100 quintillion. 100. So this, yeah, 18 zeros is quintillion. 1, 2, 3, 4, 5, 6. So that's 100 quintillion. So 18 zeros is quintillion. All right. So that is, we have 100 quintillion sequences. Clearly, exploring every possibility is impractical in that case. So the question becomes, how can an AI search intelligently instead of search? How can an AI search intelligently instead of searching everything? That is where the AlphaGo architecture becomes fascinating. So let's look at the AlphaGo strategy then. The broad idea can be summarized as follows. You have the Go board, you have the policy network, the promising moves, you have the Monte Carlo Tree Search, and then you have policy guidance and policy evaluation leading to the best move. And the neural networks guide the search, and the search improves decision quality. So the resulting experience can then be used to improve the models. This creates a powerful feedback loop. So let's talk about self-play now. One of the most important ideas is self-play. Instead of requiring humans to provide every training example, the AI can play against itself. So the process is AI plays against itself and generates games, observes wins and losses, then learns more outcomes, and becomes stronger and then plays stronger games and learns again. So that's like, and that's the whole idea of artificial intelligence. So without supplying, so you just said once you set machine learning or AI in motion, so it improves itself based on new evidence, based on new data that it gets. So this creates an iterative improvement process in that case. So why self-play is powerful? Suppose an AI starts with a weak strategy, it plays itself, the game contains mistakes, then the games contain mistakes, right? The AI learns from the outcomes. After training, it becomes slightly stronger. Now it plays against its improved version. The new games become more sophisticated. So this produces a cycle: weak policy, self-play leading to training, training leading to better policy, self-play again, and the policies get better and better. This is one of the deepest ideas behind modern game playing AI. Self-play, right? Because the AI plays with itself, and that is why sometimes it can win the best of champions in any kind of game. Exploration through self-play. Self-play also creates opportunities for exploration. So suppose the AI always selects its highest probability move, it might become trapped in a narrow strategy. Instead, training can introduce controlled variation. So the model explores alternative actions and can discover strategies that humans might not have considered. This is particularly important in games such as Go, where unconventional strategies can be extremely powerful. Okay, then we have temperature and exploration. A policy network produces logits Z sub I. So a softmax converts them into probabilities. You have P sub I. I think we've used this a couple of times, especially when we're talking about attention. So, and we also did a video on temperature because temperature helps creativity. So you have P sub I equals E raised power I Z I, E raised power Z sub I over tau, then summation over J of E raised power Z sub J over tau. Here, tau is the temperature. When tau is I, then that's big tau means more randomness, and small tau means more concentrated decisions. So thus temperature provides another mechanism for controlling exploration. So if you because the higher tendency, okay, I mean to explore, right? Temperature can help to explore. That's basically what the idea is there. So for softmax, softmax example, suppose two actions have logits z1 is 2, z2 is 1, with tau equals 1. So we obtain p sub 1. So tau equals 1 simply means the temperature is 1, and it's as good as we don't have temperature like that. So pi is now e raised power 2 based on what we have here. So e raised power zi over tau. That's e raised power 2 over 1. So that's e raised power 2 all over e raised power 2 plus e raised power 1, and that's approximately 0.731. Therefore, P2 now will be 1 minus 0.731. That will be 0.269 because they must add up at the end of the day by the time you uh, pass it through. So the first action is preferred, but the second remains also possible like that. So when you increase the temperature now, you can have the probabilities can then get close. So there'll be equal chance of the two actions taking place. And this is the demonstration for that right here. So for varying temperature, so you have 2 and 1. So then the softmax temperature, you have the logits and the temperature. So the scaled one, you have the logit over the temperature, and then now take the exponent of the scaled values and you subtract the scaled here, for some balancing. And so you have possible temperature 0.5, that's less than 1. You have 1, which is as good as no temperature, and then 2.0, which is higher, and then see the impact now. So for temperature 0.5, probabilities are 0.8 and 0.1. So lower temperature causes it helps to it causes clear demarcation in decision making. So here now it tells you action one is most likely what you should be going for because the other probability is low. But when temperature is 1, which is like moderate, then there's a bit of spreading out happening. This is 0.73. Though this is still sharp, but this is a bit the probability here is up, is a bit high up. Then temperature 2. So this one, the gap is beginning to close. In fact, what if I add temperature 3.0? So you can even get to a point where the two actions have equal chances. So here now you have 0.58, 0.41. So, let me even add 3.5. So as the temperature increases, there'll be equal likelihood. So you have a flip over here. So yeah, so you that kind of thing. You have a flip over here now. So as the temperature increases now, you keep having like that. So the probabilities are really close now that the temperature is 3. and 3.5. So optimization and the loss function then, of course, one thing we do in AI is you want to keep reducing the loss function. You want to minimize the loss function. That's why it is an optimization problem. So optimization and the loss function. Learning requires an objective. So suppose the network predicts a value v cap v hat, right? While the actual game result is z. So a simple value loss would be z minus v cap all squared. That's the square of the error. For example, z is 1 and v cap is 0.5. So LV is 1 minus 0.6 squared. That is 0.4 squared, which is 0.16. The network should adjust its parameter to reduce this error. So this error, depending on the level of error you want. Maybe you want your error to be like 0.001. So you have to go back through the process of backpropagation or whatever you have to do to get it close to zero. So here now, combining policy and value learning. Conceptually, a training objective can combine policy and value loss. And value loss is so loss is now loss in policy, lambda times the L value, lambda 2 times L regularization. So the exact architecture and training procedure can be more sophisticated, but the conceptual structure is total loss is equal to policy error plus value error plus regularization, which this represents. So the optimizer then searches for parameters that minimize this particular objective. Then we have gradient descent. Suppose L of theta is the training loss, right? Gradient descent update the parameters according to theta sub t plus 1 equals theta sub t minus alpha grad sub theta L of theta sub t. So the gradient tells us the direction in which the loss increases most rapidly. Therefore, we move in the opposite direction. That's why it is gradient descent. So this gives the intuition that move downhill on the loss surface because you want the loss to be as small as possible, basically. That's why we use gradient descent. So suppose L of theta is theta squared, then dl d theta is equal to 2 theta. So if theta is equal to 5 and alpha is 0.1, of course, then we have the new value of theta will be the old value of theta minus the learning rate 0.1 times the gradient. That's 2 times 5 now. dl d theta is 2 theta because L squared, of theta is theta squared. So dl d theta is 2 theta. 2 times 5 is now 10. So now you have the new value is 4. So that's an improvement because you want to minimize the loss. So the new value of theta is 4. And so this parameter moved towards the minimum. And the minimum is theta. Of course, when you plot theta squared or like x squared, you get a parabola that is passing through 0. So that means that the minimum. So when you keep at it, you're going to get 0 at the end of the day, or something pretty close to 0. And that's exactly what is demonstrated here. You have theta is 5.0, you have alpha to be 0.1, that's the learning rate. So this alpha, it must not be too big. If it is too big, it can cause oscillations, but it must not be too small because it can be too slow if it is too small. So for step in range 10 now, so you have gradient 2 theta, theta then is theta minus alpha times gradient. Then you print the values step by step. So step 1, you have 4.0, just like what we have here. And step 2, you have 3.2. So you keep doing the process. Step 10, you have 0.5369. So you can see how slow this is. But if we have like, let me see, if we make it like 0.5, so it will move. So in this 10 steps, so you can see it, if I from step 1, it has already got to 0. So that's too, I guess that's a bit too fast. So let's try like 0.2. So for 0.2, you're already, hitting on 0 around here. So if the learning rate is 0.25, it's also faster here. So, but if you do 0.1, you need more steps. So let's say you may need like, let's see how many steps. If I make it 20, so in fact at step 20 you are still not at 0, so let's make it like 50. Let's make it 50. So now so now even at 50, you are now like at 0.0001, like that. So the learning rate and the number of iterations will help you see some clear pictures. So the three big ideas we are talking about here, the AlphaGo story can now be reduced to three mathematical ideas. We have the reward. The agent asks, did this strategy lead to success? Optimization, the agent asks, how should I change my parameters so that I can get that success I want? Then exploration. So reward, optimization, and exploration, basically. So the agents ask, what if there's a better strategy I have not discovered yet? So that leads to exploration. Together, learning can then be reward plus optimization plus exploration, basically. So that's how learning takes place. So a simple reinforcement learning environment can be this. Let's create a tiny game. The agent starts at position 0. Its goal is to reach position 4. So, and there are two actions, left and right. So reward is plus 10 for reaching the goal. Every ordinary step receives -1. All right. So this encourages the agent to reach the goal quickly in that case. So imagine the simple game. We do object-oriented programming here, OOP. So we define a class, simple game, and then we initialize that game. Self position is 0, and the goal is 4. And then we do the reset. So self position is 0, and then return to self position. Then define step. If action is right, self position takes one, is +1. Else, if action is left, then the self position is -1. So if you go right, you get 1 point. If you go left, you get -1. Then self position then takes the maximum of 0 and the minimum of self position and self goal. So if self position is self goal, then the reward is 10. That means you have reached the goal. And then if that is done, you have true. Else, reward is -1, and then done, false. So it means you have not reached you have not hit it. So here now, this has been run, and the goal, what you expect it to return is self position and reward, and whether it is done or not. So let's talk about a Q learning, the tiny game. So we're still talking about the game. So you can see we have not got a result here. So let's talk about the Q learning. Now we can use Q learning to discover the optimal strategy. So the algorithm repeatedly observes the current state, chooses an action, receives a reward, observes the next state, updates the Q value. This gives the agent an opportunity to learn from experience rather than being explicitly told which action is correct. So we import random because we want to use some random action. Then states are, maybe we say we have 5 states. So actions, left and right. Then we have Q states. You have action 0.0 for action in actions. Then for states in states now. So let's say alpha is 0.1, gamma is 0.9. That's the discount rate. And then epsilon is 0.2. And then the environment, we have the simple game, we call it. So for episode in range, in 1000, so then state is reset. So for step in range 50, if so, the kind of thing we did before, if random.random is less than epsilon, and then uh action action is equal to random.choice actions. Else, action is the maximum of the Q state and key Q state dot get. The next state, reward and done, will be inspired by that action. So the best future can then be determined here. And then we have the target times reward plus gamma plus best future. And then the Q state and the action, is incremented, is updated constantly like that. Following that kind of that repeated increase, and then at a point you have state equals next state. If done, then you break. So we run this also. Of course, we don't get a result here yet. Then we still have the next level where for states in state now, the best action would be the maximum of Q state, key Q state dot get, then print state, Q values, and all that. So that is Q learning happening there. And when we do that, we have our state 0 Q values. So you move left, you have 3.1 to right, 4.7. Best action is actually right because right is higher than left. Then state 1. Python's counting start from 0. So we have 5 steps, but it starts from 0 and it stops at 4. Then state 1 now, which is like step 2. So left is 3, right is 6. So right is fine. So we have all of this now. So at the end of the day, by the time we are done here, so our state for Q values, left is 0, right is 0. So the best action is left because, I mean, they are more or less the same. So from tiny Q learning to AlphaGo now, the scale changes dramatically. So because what we have here is just a toy model. So for AlphaGo, it's really enormous. So the scale changes dramatically. So simple reinforcement learning, you have a small state space, but for AlphaGo, you have a normal state space. Few actions in simple RL. For AlphaGo, you have hundreds of possible moves. Q table, here you have neural networks. Then simple exploration happens in simple reinforcement learning. For AlphaGo, you have tree search plus policy guidance. You have few episodes in RL. You have massive self-play in AlphaGo. You have simple environment in RL, and you have complex strategic game in AlphaGo. So the mathematics evolves, but the fundamental idea remains the same. State leads to action, action leads to reward, and there's an update in state once the reward is obtained. Then why neural networks were necessary? Why do we need neural networks for AlphaGo? A Go board cannot realistically be represented using a gigantic lookup table containing a value for every possible state. Instead, a neural network learns an approximation. V sub V for the parameters of the neural network at state S is approximately the actual V at state S for the Go board. Similarly, a policy network learns pi sub theta. This is the neural network part now. when you see theta, it's talking about neural network parameters, which can be thousands and or even hundreds of thousands or millions even. So pi of theta of alpha given s is approximately pi of alpha given s. So the neural network therefore acts as a function approximator. So instead of memorizing every possible board, it learns patterns that generalize across positions. Then we have representation learning. A Go board contains spatial structure. A neural network can learn patterns such as connected stones, groups, liberties, territory, threats, captures, influence, strategic formations. The network does not necessarily need humans to explicitly program every strategic rule. Instead, it can learn useful representations from data. This is a major reason deep learning transformed game playing AI, right? So we have the AlphaGo feedback loop now. A useful conceptual model is we have that here, right? So imagine we have the board position, then we have a neural network which works on the policy and the value, and then leads to a Monte Carlo search, and then we have a selected move, and the game is played, and then a reward is obtained, and then training data, then we have improved network. This is the core conceptual trick of the AlphaGo feedback loop, like that. And then we have search and learning reinforce each other. So this is an important distinction. Learning improves the model's understanding of the game, while search improves the immediate decision. So it's more like in previous cases where we talked about prediction and learning. Prediction and learning. So when you make one prediction, that's forward propagation. But back propagation is the process of correcting, improving the parameters to ensure that the loss between the predicted value and the actual value is minimized. So the policy network says this moves look promising. The value network says this position looks favorable. So Markov chain training search is actually says, let me investigate these possibilities before committing. So the final decision is therefore more informed than a simple neural network prediction. So overall, we have a useful mathematical overview. We can think of the decision process approximately as maximizing a star, maximizing the action over all the possible actions. So we have a Q search for the state and the action plus the exploration bonus. So the set value is informed by simulations, policy predictions, and value estimates. And the exploration term prevents the algorithm from becoming overly confident in insufficiently explored actions. So this is a recurring theme in modern AI. Prediction tells you what seems likely. Search investigates what would actually happen. Now, why is exploration so important? Imagine an AI has discovered a strategy that wins 70% of games. Should it stop searching? No, there might be another strategy that wins 90%. So if the AI only exploits what it already knows, it may never discover the superior strategy. Therefore, learning requires uncertainty management. So to learn, you have to explore, you have to, walk in uncharted paths. So the system must balance when to trust existing knowledge and when to investigate alternatives. And that's also you want to manage that's some kind of risk management. So you need to know when to stick to what you know or when to actually try out something new. So exploration often changes during training. Early in learning, exploration should be relatively high. Later, exploitation becomes increasingly important because exploration has helped you to learn so much. So a simple exploration schedule could be epsilon sub t is the maximum of the minimum epsilon, and e sub theta e raised to minus kt. So this can help you to explore correctly. So this gradually decreases the exploration. For example, imagine the initial epsilon naught is 1, and the minimum value of epsilon so far is 0.01. So the agent starts highly exploratory and gradually becomes more confident, as we can see from here. So you have the episode like 1000 episodes, first epsilon is 1.0, minimum epsilon is 0.05, and you take a k of 0.005. Epsilon is the maximum of minimum epsilon, and epsilon times the exponent of minus k and times the number of episodes. So if you run this now, you get this. So as the episodes are going, you have the epsilon values. So with increasing episodes, you have smaller and smaller values of the epsilon. So you start exploratory and you become more exploitative as it goes on. Then we have reward shaping. So sometimes the final reward is too sparse. Suppose Go only provides +1 for winning and -1 for losing. The agent may have difficulty learning which intermediate actions were useful. In other environments, designers may introduce intermediate rewards. For example, R sub T is R goal plus R progress. So, the reward for the goal plus the reward for the progress. However, reward design must be handled carefully because that really matters. So, poorly designed rewards can cause an agent to optimize the wrong behavior. So, for instance, if a child does not behave well and you still give them money just to think that they will do the right thing. So they may feel that, oh, it's better to do bad so you can keep getting money. So some you may want to give them money to change their bad behavior instead of letting them do a good action to give them or withdraw the funds from them when they behave badly. So this is called reward hacking. In that case, reward hacking is when poorly designed rewards cause agents to optimize the wrong behavior. So reward hacking example, suppose an AI robot receives +1 for every object it collects. The intended goal is to collect valuable objects, not just any object. So, but if the environment gives equal rewards for all objects, the robots may learn to collect thousands of worthless objects instead of completing the actual task. The agent has technically optimized the reward in that case, but it has failed the intended objective. This teaches an important lesson. The reward function defines what the agent actually learns to optimize. Then we have the sparse rewards and long-term planning. Games such as Go demonstrate an extreme form of sparse reward. For much of the game, R sub T is zero. Many of the moves you make, you don't get a reward until you really win. Only at the end do we receive something like R sub big T equals R at the terminal time. +1 is win, -1 is loss. Therefore, the agent must connect very distant actions to the final outcome. This requires value estimation, temporal credit assignment, search, exploration, and repeated experience. Now, why search helps sparse rewards now? Suppose a move does not immediately produce a reward. The agent can still investigate its consequences. For example, A leads to A1, A1 leads to A2, and then you have the winning position at the end of the day. Search can identify that move A event. Search can identify that move A eventually leads to a favorable outcome, even though R of A is equal to 0. So this makes search especially valuable in strategic environments. So we talk about decision quality now. A simplified decision score can be written as this. Decision quality is approximately value estimate plus search information plus exploration. In more practical terms, good AI decision is prediction plus planning plus learning. So this principle extends far beyond board games. I mean, we've seen similar patterns even in previous videos, even when we are not talking about gaming, even in the context of natural language processing or even uh no, autonomous cars and things like that, self-driving cars. Then we have reinforcement learning beyond Go now. The same ideas appear in many AI applications. So in robotics, the state can be the robot's configuration, the action can be the motor command, and reward can be the task progress. Then we have autonomous vehicles, which I just mentioned. The state can be the road and traffic state. Action can be steering, braking, or even acceleration. And then the reward is safety plus progress towards the destination, right? And you have recommendation systems. So the state can be the user context. I think we made something about recommendation systems for Netflix and all that, which can also be extended to like YouTube. And the action is the recommended item, and the reward is engagement or long-term satisfaction because the right user is matched with the right recommendation, maybe the right movie or the right restaurant or things like that for recommendation systems. So the Markov decision process now, a reinforcement learning problem can be represented as a Markov decision process, MDP. So M is SAPR gamma. So where S is state space, A is action space, then P is transition probability, R is the reward function, and gamma is the discount factor that we saw before. So the agent seeks a policy pi of A given S that maximizes expected return. So the Markov property then comes into play there. For the Markov property, a Markov decision process assumes that the future depends on the current state rather than the entire history. That's what Markov property is. So the next state depends only on this state. Previous states don't matter. So mathematically, probability of S of the next state is given the previous state and action, the immediate past state and action, and the one before the state before that and the action before that. They don't, at the end of the day, everything just boils down to probability of the next state given just the current state and the current action. It doesn't matter what state and actions we had before this point. So that's the Markov property. In what, once we know the current state and action, this earlier history does not provide additional information about the next state. So a well-designed game state contains the relevant information required for decision making. Then we have the complete reinforcement learning pipeline. So far, we can now connect everything. So we observe the state S of T and we predict promising actions pi given parameters theta for action given the state. Then we explore possible futures using things like Markov chain tree search, and we estimate outcomes based on V sub theta of S, and we choose an action that's A sub T, and we receive a reward R sub T plus 1. Update the model using gradient descent as we have here. Then we repeat the process. So we have observe, you observe, you search, you act, you reward, you learn, and then you rinse and repeat, like they say. Then what made AlphaGo special? The breakthrough was not simply using reinforcement learning. It was a combination of several techniques. AlphaGo is approximately deep learning plus reinforcement learning plus search plus self-play. So each component solves a different problem. So for which moves look promising? So a problem which moves looks promising, policy network takes care of that. How good is the position? Value network takes care of that. What happens several moves ahead? MCTS, Markov chain training search, takes care of that. How do we improve? Optimization takes care of that. How do we discover alternatives? Exploration takes care of that. Where does training data come from? Self-play. So from self-play, you learn. So self-play, you can consider self-play as, you playing a game, all by yourself, or just thinking about some things deeply on your own, and then you get new data from that place. So the deeper AI lesson we have from Go now is this. So the AlphaGo story reveals a powerful general principle. A model does not have to know the correct answer immediately. Instead, it can make a prediction, explore alternatives, evaluate consequences, receive feedback, update its beliefs, and repeat. This is much closer to decision making under uncertainty than ordinary supervised prediction. So the final mathematical summary is as follows. You have the key equations. Can I fit everything in one place? Okay, let me just go step by step. So the key equations, yeah, for the return now, the discounted return, like we saw. So G sub t is summation from k equals 0 to infinity of y gamma raised by k r sub t plus k plus 1. For the value function, you have gamma given the policy pi at state s gives the expected value of the discounted return at state s. And action value, you have that too. So you have both state and action determining that. Then you have the Bellman equation, which is associated with a concept. So you have you have this Q learning, you have this UCT, you have this. So that talks about exploration and exploitation. Then the gradient descent, of course, which helps in the process of learning. And you have the policy objective, like that. You want to get the best parameters that give you the best policy, the best returns. So AlphaGo formula to remember now. If you remember only one conceptual formula from this lesson, remember strong decision is learn policy plus value estimation plus search plus exploration. And the learning loop is state, action, reward, optimization, better policy. That is the reinforcement learning trick behind AlphaGo. So you can have to look at this mini project, build a reinforcement learning agent, a useful hands-on project to build an agent that learns to navigate a grid. The environment can contain, you have S, X, X, G, and you have all these dots here. So S is starting position and G is the goal. So starting from S, you want to get to this point. And X, these X's are the obstacles, and all these dots are the free space. So the agent receives a reward of plus 10 for reaching the goal and minus 1 for every wrong step, every ordinary step. So an ordinary step is a step that is not going towards the goal. Then implement, you can do it now, you can then do a Q table in initialization, epsilon greedy action selection, environment transitions, reward calculation, Q learning updates, exploration decay, evaluation of the learned policy. The final goal is to observe the agent gradually move from random behavior toward a reliable path to the goal. So we have some key takeaways. So reinforcement learning learns from consequences. That's why it's called reinforcement learning. So if you do well and you get rewarded, you want to keep doing more of that. If you do wrong and you don't get rewarded good for as you would like, you stop that action. So rewards define what the agent is trying to optimize. Then the return capture long-term consequences. Value functions estimates how promising states are. Then Q values evaluates actions in particular states. Optimization changes model parameters to improve performance. Exploration prevents the agent from becoming trapped by its current beliefs. Monte Carlo Tree Search provides structured exploration. Policy networks guide the search toward policy promising actions. Value networks estimate the quality of positions. Self-play generates training experience without requiring humans to label every move. AlphaGo strength came from combining learning, search, optimization, and exploration. The same mathematical ideas now appear in robotics, recommendation systems, autonomous systems, and other sequential decision problems. The deepest lesson, intelligence is not only predicting what happens next, it is learning which actions produce better futures. So we have our practice problems, and I get to solve two of them. Let me see. This has been a long video, but let me see if I can still solve some problems. Okay. Um, so I like to solve 13 and Questions 13 and 17. Question 13 and 17. Okay. Now, here you can see problems 1, 1 and 2 clearly. Then 3. Can we see 3 and 4 here? 3 and 4. So 3 and 4. 5. Okay, 5 and 6. 5 and 6. 7. Okay, only 7 and 8 can be seen here. 7 and 8. 9 and 10. 9 and 10. 11. We can see 11 and 12 here. Then 13. So I'll be taking care of 13. UCT comparison. A search node has visited 200 times. A search node has been visited 200 times. For two possible actions, A is W is 90, N is 100, and B, W is 42, N is 50. Let C be 1.2. Calculate the UCT score for each action. Which action would the search select? Okay, so I'll be solving that. Then the other one I'll be solving will be 17. So, but here you can see 13 and 14. Okay, 14 cannot even be seen clearly. So let's just stop at 13. We see 13 here. 13, then 14. So I think we should be able to see 14 and 15. Okay. 14, 15, and 16. 17. I'll be taking care of 17. A policy network produces logis 3 to 1. Calculate the softmax probabilities for tau is 1 and tau is 2. Compare the two probability distributions. Which temperature produces greater exploration? Of course, higher temperature means greater exploration, even without solving yet. So you can see 17 and 18, and then 19 and 20 is pretty long. So you can see, let's say 19 and a part of 20. Okay, 19 and a part of 20. Then the whole of 20 can be seen here. So let's go and quickly do that as we bring this video to a close and also bring the whole playlist on the mathematics of artificial intelligence to a close. This has been a very interesting journey for me. I'm sure it has been for you too. So problem 13 now. Problem 13, we are given NS. That's number of times that particular one has been visited is 200. So for action A, W of A, wins has been 90. Number of visits has been 200. Has been 100 rather. 100. Then for action B, number of wins for B has been 42. And number of visits at B has been 50. Then the exploration constant is C, which is 1.2, like we saw in the question. So this is the data we have to start with, and we need to calculate the UCT. To calculate the UCT, we use the formula. UCT for the state and the action, that is the number of wins, S over A, number of visits, S over A, plus exploration constant C multiplied by square root of the natural logarithm of all the total number of visits, or so N of S rather, N of S all over N of S A. That's for everywhere. So, and then we take the actions one after the other. So for action A now, action A, for action A, the exploitation term, the exploitation, the exploitation term is 90 over 100, that's the number of wins that has happened. So that's win over number of visits now. So that's WA over NA, that is 90 over 100, which is 0.9. So for action B, the exploitation, the exploitation term, okay, we're still talking about A, sorry, before we go to B. So for A, the exploitation term is this, and the exploration term, the exploration term is 1.2 square root of natural log of 200 all over 100. This NSA here is still the same here, all over 100, and that is equal to, that is approximately, if you compute that, you get 0.276. Then, so therefore, the UCT for A is approximately 0.90 plus 0.276, and that is equal to 1.176, like that for action A. So let's do for action B. So for action B, the exploitation term is the number of wins for B and the number of visits for B, and that is 42 over 50. That's from the data we got originally, that's 42 over 50. So 42 over 50 means 84 over 100, as 0.84, like that. Then the exploration term, is 1.2 square root of ln 200, sorry, square root of, ln 200, all over 50. That's approximately 0.552. So that means that UCT at B is approximately 0.84 plus 0.552, and that is 1.392. So we have 1.392 for B and 1.176 for A. So that means, UCT for B is greater than UCT for A, right? So the Markov chain tree search selects action B, like that. So it selects action B. So although A has a slightly higher estimated value, right? You can see A has a higher estimated value for the exploitation. So although A has a slightly higher estimated value, B has been explored fewer times and therefore receives a larger exploration bonus. This illustrates the central Markov chain tree search. Search balances known quality with uncertainty. So that's the lesson. So the lesson we learned from here is that search balances known quality with uncertainty. And that goes. So let's take problem 17 quickly. Problem 17. So for problem 17 now, we have logits. I mean, we've done this a couple of times. The logits are Z equals 3, 2, 1, like this. So, and then we have the temperature. So the temperature controlled softmax, the temperature controlled softmax is P sub I equals e raised power Z sub I over tau all over summation over J for E raised power Z sub J all over tau there. So with that in place, what do? We take the cases now. So we have case one. We have two cases. I think we have case one, T is one, and case two, tau is one, and case two, tau is two. So for tau equals one now, so we have the scaled logits. The scaled logits remain. The scaled logits remains 3, 2, 1, because if you divide each one by 1, you still get the values. Therefore, we have the P1 to be e raised power 3 all over e raised power 3 plus e raised power 2 plus e raised power 1. That is e raised power 3 all over e raised power 3 plus e raised power 2 plus e raised power 1. And that's approximately 0.665 if you compute properly. And that means, and that gives P2. If you do P2 also, P2 will simply be e raised power, so this is 1, 2, 3. So P2, that's e raised power 2 all over e raised power 3 plus e raised power 2 plus e raised power 1. And that's approximately 0.245. And then you have P3, which is approximately e raised power 1 all over e raised power 3 plus e raised power 2 plus e raised power 1. That's 0.090, like that. Thus, so the probability with at tau equals 1 is approximately 0.665, 0.245, and 0.090, like that. So that is for tau 1. So in this case now, you can see this is remarkably the outstanding one, then followed by this and followed by this. But then let's see what happens with a higher temperature, a temperature of 2. So, what we have here is this, that the first action, right? So the first action, so here, the first action is strongly preferred, strongly preferred. And then we go for this case 2. So for case 2 now, we have tau to be equal to 2. So in this case, the logits become 3 over 2, then 2 over 2, then 1 over 2. And that is the same thing as 1.5, 1.0, and 0.5. So because now tau is equal to 2, so we now have scaled logits in that case. So with that in place, so the resulting probability, so if you do the same process, right, in that case, you get probability at 1, right? That's approximately e raised power 1.5 all over e raised power 1.5 plus e raised power 1.0 plus e raised power 0.5. That's approximately 0.506, like this. Then P2 is approximately e raised power 1.0 all over e raised power 1.5 plus e raised power 1.0 plus e raised power 0.5. That's approximately 0.307. You want to check this. Let's, in case anything is not right, please let me know, but I believe it should be right. So you have e raised power 0.5 now all over e raised power 1.5 plus e raised power 1.0 plus e raised power 0.5, and that's approximately 0.186. So you can see the probabilities are a bit closer. Here we have 0.6, 0.2, 0.0, but here you have 0.5, 0.3. So they are a bit closer together now. So overall, right? Overall, probability for tau equals 2 is approximately 0.506, 0.307, and 0.186. Please confirm to be sure these calculations are right. So here we see that here the distribution is now much flatter. So there's a higher chance of taking any of the 3 actions now, although the first action is still clearly distinct. Therefore, increasing temperature from 1 to 2 increases exploration because probability is spread more evenly across the available actions. I think I want to write that. So therefore, increasing temperature So for text, for natural language processing, right? Temperature calls for for diversity, for it avoids things being monotonous. Therefore, increasing temperature from 1 to 2 increases exploration. So if you want to increase exploration or creativity, uh, you go for higher temperature. From 1 to 2 increases exploration because because probability because probability is spread more evenly across the available actions. So in general, when tau increases, increased tau implies more exploration, more exploration, while when tau goes down, we have more concentrated decisions, more concentrated, more concentrated decisions. So this allows game playing AI, game playing AI to control how deterministic, or exploratory its move its move its move selection becomes. Okay, so with that we come to the end of this interesting video on AlphaGo, the reinforcement learning trick that is behind AlphaGo, like that, the learning trick behind AlphaGo. So it's all about reinforcement learning. So you do an action, you get a reward, and then that helps you to do to know how to do the kind of actions you want to make to always get the kind of reward you desire. So I'll show the problems again so you can try your hands on them and see how well you get it. So here, can we show 1, 2, 3? I think I can. So here you can see problems. Okay, it's hard to show 1, 2, 3. Let me just show one, focus on 1 and 2. So you see 1 and 2, 1 and 2, then 3 and 4. You can see 3 and 4, 5 and 6, 7, 7 and 8. Yeah, you can see 7 and 8, 9 and 10. You can see 9 and 10 here. Then 11, 11 and 12, 11 and 12. 13, 14 is a far cry here. So I did this 13. So this is the question, the first question I solved 13. Then 14, this is 14 now. 15. Guess we can see 15 and 16 together. So you have 15 and 16 here. 17 and 18. Then 19. Okay, let me expand 19 because 20 is really large. So this is 19. I remember I did 17, right? I did 17. Comparing temperatures. Then, I mean, when we say temperature, we're not talking about heat like that. We're talking about that thing in AI that helps diversity, that helps exploration. So this is 20, so this is designing an AlphaGo-like decision system. Let me know how helpful this is for you. And if there's something else you let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? So why not subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Having known that, you can also become a member of the channel by clicking on join. That gives you special privileges that you find out when you click on join. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.